All right, good morning. Looks like my computer's been fighting me every step of the way this morning. Okay, how was the weekend? Exciting? Yeah? Glad to be here? All right, anyways, so we're going to continue our discussion of, or our derivations of the molecular partition functions. What we've done thus far, monoatomic ideal gases, the average energy of a system is given by the kinetic energy, 3/2 NKBT, plus the electronic contribution to the energy, and that's the energy above the ground state. We've pointed out on numerous occasions, and you showed in calculations, that you're not likely to populate an excited electron, an electronically excited state. Therefore, this is usually pretty close to zero. And then once we have the energy, we can take the derivative of the energy with respect to temperature, and that can give us our heat capacity. If we assume that our energy above the ground electronic state is equal to zero, then we're just worrying about the translation. So this basically tells us when we increase the temperature of a system, all this energy is going to be transmitted into kinetic energy. All right? And then we've changed our discussion to diatomic ideal gases. So we've shown that, or we've pointed out that the translational partition function is exactly the same as it is for a monoatomic ideal gas. And the last time we met, we showed that we could write the vibrational partition function as this analytic expression. So in terms of beta, in terms of temperature, and then we've introduced this vibrational temperature, which again is just done as a convenience to reduce the number of variables. Right? And that's what that next point states. So some things that we just want to remind ourselves, and at this point, these should be pretty natural to you, and you should be comfortable with this. So the probability of being in a particular energy level is proportional to the Boltzmann factor. And if we look at the Boltzmann factor, if we have temperatures going up, that's going to reduce the size of the Boltzmann factor, or that's going to increase the size of the Boltzmann factor. As temperature approaches infinity, as that goes to a really large value, then this goes to 1. All right? And then as the energy goes up, that is the energy level spacing, as those energies increase, we see that we decrease the probability of being in those states. So we're going to talk about rotational partition functions today. So we need to remind ourselves of what the energy levels that are available to the system are. That's given by this. The heat capacity, we may get to this today or not. Because it's going to be a function of the change in the energy due to the change in the temperature, we know that energy can be split out into the kinetic energy of the particles. It can be split out into the vibrational energy and the rotational energy. So we can see that there's going to be 3 contributions to the heat capacity: translation, vibration, and rotation. All right? I say I did not correct this yet. Oh, no, that's all right. So if I have a summation of e to the minus x, where x is a small value, we can replace that summation with an integral. So we're going to be doing that today. And then we've already taken the integral of e to the cx on numerous occasions. We're going to be doing that again today. Okay? All right, so questions for this lecture. What's the rest of the partition for the diatomic gas molecule? So we've already done vibrations, we've already done translations, so we're left with the rotations. From there, we're going to ask how many molecules are in the ground vibrational state, how many are in the ground rotational state, what's the partition function of the rotational rotation, or what's the partition function of rotational energies. And then we're going to introduce, again, to just make things a little bit cleaner whenever we write down our equations, we're going to introduce what's called a rotational temperature. All right, it just reduces the number of variables that we need to write. And then we'll talk about what states are occupied whenever we're at room temperature. All right, and then if there's time, we'll get to a discussion of partition functions for molecules. Or for polyatomic molecules. Okay? All right, so where we ended last time was we showed that this is our vibrational partition function, right? And now that we have an expression for that, we can calculate the energy and the heat capacity, and that's what we'll go ahead and do. So just, we've seen this before. My system energies, so this is an ensemble of systems. the average energy of that ensemble, everybody the same number of particles, same volume, same temperature, is going to be given by the average vibrational energy for our particle in our system times the number of particles, all right? And that's going to be nkBT squared times the partial of the natural log of Q with respect to T, okay? All right, so let's go ahead and do that real quickly. All right, so I'm going to start by looking at the natural log of the partition function, all right? So we see that here's our partition function. I have a numerator and a denominator, so I'm going to take the natural log of the numerator first. So that's going to be the natural log of the exponential function. They're inverse functions with respect to each other. That's going to leave me with minus theta over 2t. All right, and then I have the denominator, so that's going to be minus the natural log of 1 minus the exponential of minus the vibrational temperature reference to the temperature. Okay? All right, and then we have to take the derivative of this with respect to t, all right, and that's what we'll do next. All right, so the derivative of the first term, well, we look at the first term, that's going to be equal to minus the vibrational temperature over 2, that's a constant, and then I have to take the derivative of t to the minus 1, that will be minus 1 over t squared. Again, we've done that previously. I've got two negatives, so then I can take the positive, all right? From that, I'm going to take the derivative of the natural log of this function, so that's going to be the reciprocal of that function. I've got 1 minus e to the minus vibrational temperature over t, all right? And then I have to take the derivative of this function. Well, the derivative of 1 goes to 0, and then I've got the derivative of minus this exponential function, so I get that back, all right? So that's going to become minus e to the minus theta vib over t. And then I have to take the derivative of this with respect to t, so minus theta is a constant, so that's the derivative of t to the minus 1, and so that becomes plus the vibrational temperature over t squared. Okay? All right, and because I have a negative, that second term goes to a positive. We all on board? Okay? All right, keeping in mind that this is the partial of the natural log of the partition function, I need to multiply that through by kBt squared. And what we see is that we've got t squared in the denominator in two places, here and here. So when we multiply that through, that's going to cancel, all right? The other thing that we notice is that we've got nkb, it's a constant, so we can keep that out front. So my first term will be the vibrational temperature over 2, and then my second term will simply be the rest of this, theta vib times the exponential over 1 minus the vibrational temperature over t. Does that make sense? All right, to make this consistent with what you see in the textbook, I want to do one other manipulation. I'm going to multiply this fraction by 1, all right? Okay. And when we do that, let's see, this is going to get me n, whoops, that's a kb, but that's okay, n kb times our vibrational temperature over 2 plus, all right, what happens to the numerator? What happens when I take e to the theta vib over t times e to the minus theta vib over t? That goes to 1, right? All right? So this is simply going to be the vibrational temperature over, and now I have e to the vibrational temperature over t minus 1. Okay? All right. And then just to remind ourselves, this first term is going to be the 0-point vibrational energy, and then the second term will be the energy above the 0 point. Okay? And then the second term above. Okay? All right, so we have an expression now for the vibrational energy of our system that's due to the vibrational energy of the particles that make up our system. Okay? All right, and then what we can do is say, well, what's the heat capacity? And we know that the heat capacity is going to be given by the energy of vibration, the change in the energy of the vibration due to a change in temperature, holding the volume constant. Right? And so that basically says I take this energy, take the derivative with respect to T. All right? So that's what we've done. I've just plugged that in here. What happens to this first term? Is there any temperature in there? No. All right? So dt, d 1/2 dt goes to 0, and that means I only have to take the derivative of the rest of it. Okay? All right, let me talk through some substitutions that I've done. Because we're doing this on a per mole basis, that gives us Avogadro's number. So Avogadro's number times Kb we know is equal to R. I have this theta vibe in two places, so I can pull that out in front. And then this is just explicitly the derivative of the reciprocal of this function that we've done previously. Okay? All right. So we have this term then that results from this taking this differential. And then again, be consistent with the textbook, I'm going to do a little mathematical trick. This is multiplying by 1. All right. So what happens to the numerator there? What do I end up with? So it's e to the theta vibe times e to the minus 2 theta vibe. So that's going to become anybody? Anything? Yeah. All right. And then I was saving a little bit of mouth time by not talking about T. Does that make sense, though? When I multiply these two by each other, that becomes e to the minus 2 theta vibe plus theta vibe over T. Okay? All right. All right. Let's talk a little bit about the denominator. It's a little bit harder to see. All right. So one of the things I can say is this e to the minus 2 theta vibe is going to be the same as e to the theta vibe over T raised to the what power? 2. Yes, thank you. You guys seem to have lost your tongues today. All right. And that basically means that I can plug that right into that equation, right? So that first term is going to go to 1, right? And the second term will be the exponential of minus theta over T. 1 minus e to the minus theta vibe over T, and that whole quantity gets squared. All right? And this should look familiar because we've played with this form of the vibrational contribution to heat capacity previously. All right? We've shown that if we're at low temperatures, it goes to 0, right? So as T approaches 0, CV, vibe, goes to 0. And we've also talked about the high temperature limit, which is also known as the classical limit, and that heat capacity goes to R. So T to infinity, CV goes to R. Okay? All right. And if I need to know it in between the two, then I have to explicitly calculate the contribution to the heat capacity. All right, let's do a quick calculation on this. So in this case, we're going to be talking about the carbon monoxide molecule, 1,000 degrees Kelvin, and we want to know what the heat capacity is due to vibrational modes. All right. So what I'm going to do is I'm going to calculate out the ratio of theta vibe over T first, right? Quick quiz question, candy worthy. Where do I get these values? I hear it. Spectroscopy? Who said it? All right. What are these two? Okay. Well, we'll let you guys fight it out. Well, yeah, experiment works too. All right. It's a low bar today. Right. So, How many people thought experiment? Or how many think they would have thought experiment? Right? So pass the candy around the room. All right. We need to do something to inject some energy today, right? Okay, so at any rate, I can calculate the ratio of the vibrational temperature, where I can get that vibrational temperature from IR spectroscopy. That's going to be 3103 Kelvin. We're interested explicitly at looking at 1,000 degrees Kelvin experimentally. That comes out to be around 3.1. And that's unitless. Okay? All right, so now I have enough information to do the calculation. So I have R times 3.1 squared, and then the exponential of minus 3.1 divided by 1 minus the exponential minus 3.1 squared. Okay? All right, so just a quick note, whenever you're doing these calculations, you can save yourself time by calculating these ratios before you apply them to the overall equation. And because we know that at one end we're at 0 for this contribution to the heat capacity, the other end we're in R, I think it's of interest to say, well, where are we compared to R, right? And it turns out that it comes out to be around half of R. Whoops, that's supposed to be a 7. Okay? All right, so for this molecule at 1,000 K, my contribution to the heat capacity is about R over 2. Right? And in terms of an explicit number, that's on the order of 3.9 joules per mole per K. Okay? All right, so again, what this is saying is if I take my carbon monoxide gas, I increase the temperature, this tells me where that energy due to changing the temperature changes the energy of vibration. Okay? All right. So it may be of interest to ask what's the fraction of molecules that are in excited states. All right? And this section is actually called most molecules are in the ground vibrational state at room temperature. All right? So let's see if we can show that explicitly. We know that we have an expression for the partition function, right? We know that we have the substitution for vibrational temperature in terms of the fundamental frequency. So if I'm interested in a generic expression for the fraction that are in a given vibrational state, that will be given by the Boltzmann factor, e to the minus beta h nu times v plus 1/2. That's the Boltzmann factor for whatever state we're interested in, and then divided by Q. Okay? All right. Let's talk through the arithmetic here a little bit. This second term is 1 over Q vibration, right? And then I have my Boltzmann factor, all right? Now I can multiply beta h nu through this summation. That gives me 2 terms, and we've previously shown that we can take this exponential then and split it into 2 exponentials. Is there some way that I can simplify this at this point? We see that we've got e to the minus beta h nu over 2, and we see that we've got it in another location, right? So that's going to cancel, and I'm left with this term. Okay? All right, so this is in general, and then to put it in terms of vibrational temperature, we can say that that is the same as e to the minus v theta vib over t times 1 minus e to the minus theta vib over t. Okay? All right, so this is a generic expression that tells me the fraction that are in any vibrational state. Okay? All right, again, why don't we take a moment for carbon monoxide and do the calculation. So I'm interested in knowing the fraction of carbon monoxides that are in the ground state at room temperature, 300 Kelvin. All right? So we're going to do the same thing. We know from experiment 3103 is the vibrational temperature of carbon monoxide molecule. and then I'm going to divide it by the temperature, 300 Kelvin, and the ratio of those two comes out to be 10.3, right? So if I want to know the fraction that are in the ground state, I'm going to plug that information into the equation that we've just derived, right? So that's going to be e to the minus, all right, and v is equal to 0, so that's going to be e to the 0 times 1 minus, now exponential, minus 10.3, okay? And we all know that e to the 0 is the same as 1, all right? So we could do the rest of the calculation here. This is going to come out to be 1 minus 10 to the minus, 3.2 times 10 to the minus 5. All right? And what is that number essentially? It's essentially equal to 1. All right? Okay, so this really tells us that at room temperature, carbon monoxide, almost 100% in the ground vibrational state. Now, if I'm interested in knowing how many are in the first excited state, then what I'm going to do is use the same equation, but now I'm going to put 1 in for the value of V. Okay? All right. And that's going to equal e to the minus 1 times theta vibe over T times 1 minus e to the minus theta vibe over T. Okay? All right. And then what we know is that this e to the minus theta vibe over T, we've already determined that earlier, right? That's the same as this term. So that's going to be 3.2 times 10 to the minus 5. All right? And then times 1 minus 3.2 times 10 to the minus 5. All right? And we already know that this is small compared to this, so essentially we find that 3 times 10 to the minus 5 is the fraction that's in that vibrational state. Does that make sense? Okay? So we'll just say approximately 3.2 times 10 to the minus 5. Okay? All right, so we do want to talk about this a little bit more globally, and I want to take a moment to just connect this with the bond strength between two atoms in a diatomic molecule. So we've previously pointed out that if I have big diatomic atoms, right, or in my molecule, so this would be bromine, chlorine, iodine, those are pretty weak bonds. That corresponds to small values of K, small force constants. And if I have a small force constant, I have a smaller fundamental frequency. And because the fundamental frequency is directly related to the vibrational temperature, we're going to have a smaller value for that vibrational temperature. Okay? And if we think about what that means, you know, in terms of our Boltzmann factor, e to the minus theta vibe over T, that makes this a smaller number, and that means that it's going to be more easily accessible to our molecules. So what we can see is that for those specific molecules, we have a more significant population in excited vibrational states, right? So the next thing that we want to do is just ask the question, can I come up with an expression that just asks, what's my fraction in excited states, all right? We know the fraction in the V equals 1 state, V equals 0 state, etc. So if something's in an excited state, what do we know about it? What's V not equal to? It's not equal to 0. So anything other than 0 will give me the fraction of the excited state. We agree with that? All right. So we start with what we've derived previously. The fraction in a given state are given by this. Fraction in the ground state for vibrations, we've shown is going to be, well, this V initially is equal to 0. And so that means we're going to basically say it's 1 minus the exponential e to the minus theta vibe over T. Okay? Again, does that make sense? I put a 0 in for that, so that makes this 1. So I'm left with the rest of it. Okay? And then we know, as long as we're talking about the fraction of our molecules, if we sum over all the possible vibrational states, what's that sum of fractions has to be equal to? That has to be equal to 1. All right? So the fraction in excited states will be given by fraction v greater than 0, 1 minus the fraction in the ground state, right? And this is the fraction in the ground state, so 1 minus that leaves me with only that exponential term, e to the minus theta vibe over t. Okay? We good? All right, so let's take a moment to just look and see what that looks like for a series of molecules. So if we look at diatomics, hydrogen, HCl, N2, what we see is the fraction in the excited state at room temperature is very, very low. If I go to 1,000 degrees Kelvin, it's still quite low. Okay? For those molecules with strong bonds, theta vibe is in every case greater than 8,000 K. Oops, sorry, 3,000 K. I should be looking at my cheat sheet a little bit more often. All right? Now, if we look at the exceptions that we've mentioned, large mass molecules, chlorine, iodine, and bromine, we see that in this case I've got around 7% in the excited state. Here I've got around 36%. Okay? All right? And then here's bromine. This is room temperature. Well, we see, I can't even tell what that is. What is that? So it's about half. So it looks like it's on the order of 15% or so. Does that make sense? Right? And we expect that these numbers are going to track with the vibrational temperature that are reflective of the strength of the bond. In this case, the vibrational temperature is on the order of 460 K. Okay? For chlorine, this vibrational temperature is on the order of 800 K. And in this final case, iodine, right, where we see, a lot of the molecules in the excited state at room temperature, we expect that to be an even lower value, right? And that's on the order of 300 K. Okay? Does that make sense? All right, so at this point, what we can do is, as long as we have access to either the vibrational frequency or the vibrational temperature from experiment, we can determine who's in what state at a given temperature and the fraction in excited and ground states. All right. Okay, in the next section, we're going to be talking about rotational partition functions. So Q rotation is going to be a goal in this section. We're also going to say at the outset, at room temperature, most of our molecules will be in excited states. Rotational states. Okay? All right. And again, this should make some sense because we know that the vibrational energy spacing is large compared to the rotational energy spacing. Right? Okay, so from chapter 1, we know that we're going to need to know what the energy levels that are allowed are, right? And that's going to be given by h bar squared over 2I times j plus 1, and j is the rotational quantum number, and its integrals starting at 0. Okay? All right, and then just a reminder that this I in the denominator, that's the moment of inertia, and it gives us information. If I know the moment of inertia, I know the bond length, or I can calculate the bond length as long as I use the reduced mass. Okay? Okay, so the other thing that we pointed out when we introduced rotational levels for our diatomic molecules, we mentioned that there's a degeneracy, all right? So the fact that we have this degeneracy means that we're going to be doing a summation over levels rather than states for our partition function. So our rotational partition function will be the summation j equals 0 levels, all right, going up to infinity. I have to put the degeneracy term in there, 2j plus 1. Then I have my Boltzmann factor, e to the minus beta h bar squared over 2I. That whole thing gets multiplied by j plus 1. Okay? All right. And we can probably see that we're writing an awful lot of numbers. So this is where we're going to introduce something to simplify the expression a little bit. So we're going to define a rotational temperature. And that's going to be given by capital theta with ROT down below. Okay? And that's going to be the same as h bar squared over 2I kb. Okay? All right, and then before we move forward, let's just remind ourselves, we know that we can get this I from spectroscopy experiments, and this is specifically microwave spectroscopy. All right? So I from microwave rotational spectra, and then that could be used to give us our experimental value for the rotational temperature. Okay? All right. And I'm not going to bother writing this because it's not a spectroscopy course, but we also, when we introduced diatomic molecules and talked about the vibrational spectrum, we saw that we got a rotational vibrational spectrum, which means that I can also get this from vibrational. Actually, I changed my mind. I'm going to go ahead and write that down. So also from, we'll just say, or rho vibrational spectra. Okay? All right, so at any rate, we know that we can determine what the rotational temperature is. All right, and then I can rewrite this to simplify things a little bit. Summation j equals 0, again, levels going to infinity, degeneracy 2j plus 1, e to the minus, and now I'm going to introduce theta rotation over t, and that whole quantity is multiplied by j plus 1. Okay? All right. So if we're talking about room temperature, this ratio is usually small, so this is an exponential to a small number. And we've previously pointed out that in that case, what we're going to be able to do is replace the summation with an integral. All right? This shouldn't say at higher temperatures. This should say at room temperature and higher. Q rotation is the summation from 0 to infinity, 2j plus 1, e to the minus the rotational temperature over t, quantity j plus 1, and that's integrated over all j. Okay? All right, so we look at this and we say, all right, we're going to have to integrate this, and it looks a little bit messy, right? But we can see that there's going to be a little bit of an arithmetic trick that we're going to be able to do to make it a little bit less messy. So we're going to just say at the outset, we're going to let x be the same as j plus 1. Okay? All right. And if I multiply that through, that's going to be j squared plus j. Okay? All right. So if x is equal to j squared plus j, what's dx going to be equal to? 2j plus 1. and then dj, right? Okay, and now we say, oh, this is going to simplify things nicely. Jj plus 1 now becomes x, and then dj times 2j plus 1 is the same as dx, all right? So let me just write that out explicitly. So that's going to be the integral from 0 to infinity of e to the minus theta rotation over t times x dx. Okay? All right. And then we've already said at the outset the integral of this is going to be the e to the x times the integral of cx with respect to x. Right? And so for this particular example, I've just rewritten it down here below. So this is 1 over c, all right? And then this, of course, is e to the cx. Okay? So there's our integral. Everybody follow that? Make sense? Okay? All right, so now we need to evaluate it between the two limits, 0 and infinity. All right? So I'm going to rewrite. So I've got minus t over the vibrational temperature. All right? And this is going to be e to the minus infinity minus e to the 0. Okay? What's e to the minus infinity? Right? That's 1 over e to the infinity, right? So it's 1 over e to a huge number, which is 0. Right? So this goes to 0. This we know is equal to 1. And we're left with a negative of a negative, so that's going to simply be T over the rotational temperature. So we now have an explicit analytic expression for the rotational partition function. Okay? Let's see. What page are we on? 14? All right, so what I'm going to do at this point is I'm going to replace the rotational temperature, and we'll see that we are going to end up with the expression that we've seen previously. So this is going to be 2 over our 2I kb times T over h bar squared, right? And now I'm going to get rid of h bar squared. So that's going to be 2 pi squared over h squared I kb t. Right? And that's going to become 8 pi squared I kb over h squared, all times the temperature. Okay? And again, we've previously used this expression. All right? So we've shown where that comes from. Okay? All right, and then we can play the same games that we've played previously. Now that we know what the partition function is, I can say what's the energy of that particular mode and what's the contribution to the heat capacity for that mode. All right? So we're talking about, and again, every place that says room high temperature should be room temperature and higher. Right? So again, the same thing that we've done previously. My rotational energy is going to be, of my system, is going to be the rotational energy on average of the particles times the number of particles. That's going to be n kBt squared partial to ln of q rotation with respect to the temperature. All right? So here's the natural log of our partition function. The temperature is the part that's important, so I pull out natural log of t, and then I have the natural log of everything else. I take the derivative of the natural log of t. What does that give me? 1 over t, and then the derivative of everything else is 0. All right? So, and then I can plug that in, and that basically says that my energy is going to be n kb. T squared over t gives me t. And that will be my system energy. And I forgot to put rotation in there. Okay? Does that make sense? Okay, so I want to take a moment to just talk about this because this will be doing a little bit of foreshadowing. So if I'm talking about rotational degrees of freedom for a diatomic, how many are there? How many angles do I need to describe the position of a linear molecule in space? Linear molecule? Just two, right? Does that make sense? Okay, so I have two rotational degrees of freedom, right? And this energy is going to be associated with those 2 degrees of freedom, right? And that basically tells me that if I wanted to know what the rotational energy is for 1 degree of freedom, what's it going to be? This is for 2, so what do I need to do for 1? Divide it by 2. All right. If I'm talking about a nonlinear polyatomic, how many rotational degrees of freedom do I have? All right, so this is my diatomic. I have a polyatomic that's nonlinear, so I'm going to add something that puts it into the 3rd dimension. 2 degrees of freedom are required for this portion, and then I need to think about the rotation of this around that axis. So I need 3, all right? So 3 rotational degrees of freedom. And then as a consequence of that, we can say that E rotation for a nonlinear polyatomic will be what times NKBT times 3/2, right? Okay, make sense? All right, and then as we've done previously, we can say, well, what's the contribution to the heat capacity? You know, what's going to happen to the energies of rotation when I change the temperature of my system? That's going to be the derivative of this. So I come back to my diatomic, that's going to be the derivative of NKBT with respect to T, holding volume constant. We're explicitly talking about the molar heat capacity, so that's Avogadro's number, right? And that means that's going to end up being, what's my final value? It's going to be R, all right? So linear molecules. CV rotation per mole is equal to R. Let's extend this a little bit. If I'm talking about a nonlinear molecule, it's going to be how many R? It's going to be 3/2 R, right? 1/2 R per degree of freedom. Okay? All right, so we know the energy of our system with regards to rotational energies. We can do the heat capacity, do contribution to the contribution to heat capacity due to rotations. And then next up, we're going to ask, what's the fraction of our molecules that are in a particular state? Okay? So we know that the rotational partition function is given by theta, or T, over the rotational temperature. So my fraction is going to be the degeneracy, 2J plus 1, of the energy level that we're interested in, e to the minus beta j plus 1 over t. Or no, I guess the t's already in there, so let's just leave it at that. So beta, yeah. Let's do this in terms of vibrational temperature. It just makes everything easier. Rotational temperature, all divided by T. All right. And that's divided by Q rotation right? And then doing the substitution, this ends up to be 2J plus 1, our rotational temperature over the actual temperature times the Boltzmann factor, e to the theta rotational over T times J plus 1. Okay? All right, so we have an expression to determine the fraction in a given rotational energy level, right? So we'll do a quick example. So I've got a molecule AB. It's at 300 Kelvin. That's room temperature. Experiments tell us that the rotational temperature is 2.88 Kelvin, right? And for 2.88 Kelvin, we now have enough information that we can calculate everything that we need to calculate. All right, and that's what I've done here. So the first thing that I've done is I take the spectroscopy data, 2.88 Kelvin, divide that by 300, that gives me this ratio. I plug that in every place that I've got the ratio of theta over T. All right, and I've done this for a number of things. I did it with Excel to save some time. This is the fraction in the ground rotational state, fraction in the J equals 2 state. Right? And we can clearly see that most of the molecules are not in the ground state. Right? What's the maximum that we see on this particular example? Maybe around here. We agree? All right. So this shows the same sort of information. This is from the textbook. This is a carbon monoxide, room temperature. We clearly see this envelope. This is our maximum, very clear. Most of our molecules not in the ground electron or ground rotational state. Right? If I wanted to know where that maxima is, and I had this function, what would I do to that function? How do you determine maxima and minima? You take the derivative, set it equal to 0. Right? So I can take the derivative. That's my function. df of j with respect to j equals 0, and that gives me an expression for the maximum, and that comes out to be j most probable equals T over 2 times the rotational temperature raised to the 1/2 power minus 1/2. Right? You may notice that there's an approximation in here. Oh, I didn't put the approximation. I'll put the approximation in there now. Right? Can anybody tell me why they think that this is an approximate and not exact? Anybody? Right? So this is a function, right, that I'm taking a smooth curve through, taking the derivative of it. These values have to be, j has to be an integral value, right? So really what that says is that whatever you calculate here, you need to round that to the nearest integral value to get the most probable j. Make sense? All right, that's where we're going to leave it for today. Have a good one. I will see you guys on Wednesday.